In this video, I will present a proof of the quadratic formula. This proof will be based on completing the square of a quadratic equation in the form ax squared plus bx plus c. This is a quadratic equation because the degree on the variable x is 2. The quadratic formula states that the solutions for x, the two solutions for x, can be expressed in terms of the coefficients a, b, and c, namely x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This is assuming that a, b, and c are any constants with one restriction. The value of a does not equal 0. Let's begin the proof. The first step in this proof will be to rewrite the equation so that the coefficient on x squared is a 1. We're going to rewrite this so the number in front of x squared does not have a value of a, but instead has a value of 1. And this can be accomplished by dividing each term on both sides of the equation by a. Remember, we've stipulated that the value of a can be any constant except 0, so we're not dividing by 0 here. We're dividing by a non-zero value. So this is a valid mathematical step to divide each term on both sides of the equation by a. When you divide the first term by a, the result is always x squared, regardless of the value of a. The second term is bx over a. The coefficient on x becomes b over a. The constant, the third term, becomes c over a. And on the other side of the equation, 0 divided by any constant, 0 divided by any non-zero constant, is still going to be 0. Next, we're going to take the constant term on the left side of the equation, and we're going to isolate that term. We'll move that term to the other side of the equation. And this can be accomplished by subtracting that constant, whatever that value is. We'll subtract that from both sides of the equation. When you subtract it from the left side of the equation, we'll have a difference of 0. And on the right side of the equation, 0 minus c over a can be simply stated as the opposite of c over a. That brings us to perhaps the most important step in this proof, and that's where we're going to complete the square. Completing the square is a process that can be done on any quadratic, and it will allow us to factor the quadratic as a perfect square, as some quantity squared. This can be accomplished using the coefficient on x, the coefficient on the linear term in the quadratic, and in this case that coefficient is b over a. I'm going to take that coefficient b over a and do two things to it. First, I'm going to cut it in half. You can cut any value in half by simply multiplying it by 1/2. b over a times 1 over 2 would be b over 2a. Half of b over a is b over 2a. The second thing I'll do to that coefficient after I've cut it in half is square it. I'll take b over 2a, square it, and I'll express that as b over 2a squared. Now, I'm going to take that value of b over 2a squared, and I'm going to add it to both sides of the equation. On the left side of the equation, I have x squared plus bx over a, and to that side of the equation, I'll add b over 2a squared. Likewise, to the right side of the equation, I'll also add that value. Now, what I'll do on the right side of the equation is I'll actually square the numerator and denominator separately and express that as b squared over 4a squared. The reason I'm doing that is in the next step I'll actually add the two fractions that are on the right side of the equation, and it's easier to do that if I have squared the numerator and denominator separately. The next step in this proof will be to factor the quadratic expression that's on the left side of this equation. This expression can be factored because I've just completed the square. So I'm going to be able to factor the left side of this equation as a perfect square as a quantity squared. it is true that any quadratic of the form x squared plus 2xy plus y squared is equal to the perfect square, x plus y squared. Here, the first term is x squared, and the last term in the quadratic is not y squared, but it's b over 2a squared. Let's verify that this middle term, bx over a, is 2 times x times not y, but b over 2a. Well, this product has a 2 and another 2 in a denominator. So those would cancel out, and I would be left with just x times b over a, x times b over a, or the way that it's written in the quadratic expression on the left side of the equation, bx over a. So the quadratic on the left side of the equation does fit this form, so I can factor it as a perfect square. I can factor it as a quantity squared. The x will be the first term inside the factored quantity squared, and the second term will be the b over 2a. X squared plus bx over a plus b over 2a squared factors to exactly x plus b over 2a squared. Now on the right side of the equation, I'll add those two terms together. These are constants. I will add them. I'll add the two fractions by getting a common denominator. The common denominator between a and 4a squared would be 4a squared. The second fraction is already over 4a squared. The first fraction, if I would want to write it with a denominator of 4a squared, you could consider that as the denominator being multiplied by 4 and another factor of a. So you'll multiply the numerator, which is originally c, by 4 and a factor of a. Once the two fractions have the same denominator, you can add them and write them over 4a squared. So this would be negative 4ac plus b squared over 4ac. Instead of writing the negative 4ac term first, I'll write the negative 4ac term second and the positive b squared term first. In any case, the sum of negative c over a and b squared over 4a squared is equal to b squared minus 4ac all over 4a squared. Now remember, the point of this proof is to find a value for x, to find an expression that represents the value of x. The next step in that process, the next step in isolating x, would be to take the square root of both sides of the equation. When I take the square root of both sides of the equation, remember the right side of this equation is in terms of b and a and c. Those are all constants, so I'll be sure to include a plus or minus in front of that square root when I introduce it onto both sides of the equation. On the left side of the equation, I have the square root of a quantity squared. A square root and a square are inverse operations, so those will undo each other, and I'll be left with just x plus b over 2a. On the right side of the equation, I'll take the square root of the numerator and denominator separately. The square root of the numerator is b squared minus 4ac. The square root of the denominator, 4a squared, which can be simplified. The square root of 4 is 2, and the square root of a squared is a, can be simplified to 2a. And that leaves you with one step to isolate x, and that will be to simply subtract b over 2a from both sides of the equation. When I subtract b over 2a from both sides of the equation, on the left side of the equation, I'll be left with only an x. And on the right side of the equation, I have negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. There is a common denominator between these two fractions, so I'll write it as a single fraction with a denominator of 2a. The numerator will be negative b plus or minus the square root of b squared minus 4ac. And this is the quadratic formula. x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have proved that if ax squared plus bx plus c equals 0, where a, b, and c are constants and a does not equal 0, then x equals negative b plus or minus the square root of b squared minus 4ac all over 2a.